this is open for volunteer. Have you ever seen e to the minus some capital KT as coming in?
Yeah.
Where?
First order reaction.
First order reactions. That was a single first order reaction from K goes to the product. You saw that. And what you can see here is this is two first order reactions, but it has the same form. It has the same form, and there's a very good reason for that we'll do at the very end of the semester. But basically, sets of first order reactions all behave like first order reactions, in a sense. And they always give you, almost always give you these exponentials. And that has to do a little bit with eigenvectors and eigenvalues. But we'll talk about that later in the semester. Are there any questions on this? Okay, so we see that first order reactions, all sorts of neat things that happen. I tend to get answers that are exponentials, e to the minus a constant times t. And another thing is the CA zeros are all gone. There are no CA zeros in the answer. Those are characteristics of first order reactions. Once the reactions are not first order, that doesn't happen anymore. Okay.
So how do you get the dxa dt? Where do you get from there?
I copied. And this came from dCA dt, because dCA was in. Other questions? Okay, in the textbook, there's a simple derivation for a reversible second order reaction. You could look at that yourself. I'm not going to repeat this down on the blackboard. If you remember, we spoke about orders of reaction. When we spoke about orders of reaction, we said that's an experimental quantity, the order of reaction. What is the order of reaction with respect to A? What is that experiment? What does that mean, experimental? Can you please speak a little louder? I want you to define what the order means. That's the question. What does the order mean? The trend with the... What does trend mean? I want something more precise. Trend. That's vague. If this were a sociology class, we could talk about the trends. But here I want you to talk mathematics. That's the language of this class. Tell me in math. The way it depends on the concentration? The rate? Give me a formula. Any particular form of a function of CA? Okay, now let's have a full sentence. What is the order of reaction with respect to A?
It's going to be the subgroup of the order of the reaction.
The order of reaction is going to be the order of reaction. I know. I want you to define that using a different word.
That would be the coefficient of the subscript in the reaction.
The subscript. So the order of reaction is 1 because this is K1.
It's elementary, it's also stoichiometry, or
Does anyone understand English here?
The order of the reaction is the number, the power that the concentration is raised to. How
The experimental power of the concentration is raised to. We already had one quiz this class. When I ask you a definition that we had in a previous class and that we repeated in every class since then, if you don't know the definition, you're holding up a sign saying, I don't care about this class. And if you don't remember that, let me repeat it. I don't care about this class because I'm not going to look at the definitions here. And if you hold up that sign repeatedly, I will understand you don't care about the class. And then you can drop the class. The minimum you can do in a class, I don't expect you necessarily to understand everything the first time we say it. But I do expect you to go home and look at the definitions. To show me that you care about being in this class. I don't think that's asking too much to go home and look at the definitions. And if you don't understand the definitions, you ask about them. But to come here and I have to ask 3 people to get a definition, and I still don't get the definition right. The definition. That's telling me that people don't care. I feel like I'm talking to you, I don't feel like I'm talking to college students. If you want to have a quiz every class, you can have a quiz every class. I do not want to give a quiz every class. I don't want to grade a quiz every class. I'm guessing you don't want a quiz every class. But prove me right by looking at your notes before you come to class. And I don't want to be giving this speech every time, because it's degrading to give these speeches. Okay, so when we're looking at the order of reaction, sometimes the order of reaction changes as a function of concentration. Remember, it's an experimental quantity. Sometimes if I measure at low concentrations, I get one order of reaction, and at high concentrations, I get another order of reaction. Now that doesn't seem like it makes sense. Well, what is that telling me? So let's say I have a situation where I'm measuring the rate versus the concentration. And at high concentrations, I have one order of reaction. And at low concentrations, I have another order of reaction. In other words, let's say I start out, I look at concentration versus time. And initially, when I have high concentrations, the reaction looks, say, 0 order. 0 order means the rate concentration just goes down linearly with time. And then eventually, it looks like first order. It goes down exponentially with time. There's some sort of transition. What is that telling me about the reaction? Well, what that's telling, yes?
Wouldn't that mean it's not elementary?
Oh yeah, we know it's not elementary, but is it telling us more? So what might be going on here? Yes?
So, intermediate steps that there are intermediate steps that may occur during the increase in concentration.
Yes, yes, I agree. And what I'd like to suggest here is what some of those intermediate steps might combine to give you. So if we have a rate expression, say K1CA over 1 plus K2CA, which is this. Then notice what happens. At low concentrations, when the concentration is sufficiently low that K2CA is small compared with 1, then the reaction rate looks what order? First order. But at high concentrations, so first order, when the concentration is small. But when the concentration is large, so K2CA is large compared with 1, what does the order look like here? 0 order. So this kind of rate expression can capture a change of order. And of course, it doesn't have to be first power, first product. I can have an A here and a B here. And at low concentrations, it looks like to the A power. And at high concentrations, it looks like to the A minus B power. So I get a shift from low concentration to high concentration, from a higher order to a lower order as the concentration goes up. So a higher order to a lower order as CA goes up. Now, as we'll see, or as you should have seen from your homework, these types of denominators you tend to get when you have enzymes or catalysts. And this has to do with a conservation of surface sites. These types of denominators come from enzymatic or catalytic mechanisms. And they tend to come from, these denominators tend to come from conservation of enzyme or surface site. Okay, what happens if I go the, are there any questions on that? What happens if I go the other way? So let's say at high concentration, I have a higher rate, and at lower concentration, I have a lower rate. So I might start out at an exponential drop, and then for some regime, it seems to go to linear. So if I go from low to high, as CA goes up. Well, what that suggests is that I have two mechanisms. That is, I have two reactions that deplete A. A first order, say, and a zeroth order. First order and a second order. And what you can see here is that when the concentration is low, this term, K2CA, is small compared with K1. So the rate just looks like zeroth order, like K1. And when I go to high concentrations, this term becomes large compared with this, and it becomes first order. So I go from lower order to higher. And again, it doesn't have to be like this. I could have a CA to the A and a CA to the B here, where if B is greater than A, it doesn't matter. Whichever one is bigger takes over at high concentration, and whichever one is smaller takes over at low concentration.
Professor, does it also mean for reversal of reaction? Maybe the backward reaction is favored? Because when the
Here, right now, I'm trying to, from experimental data, I'm trying to infer what might be going on. There's no guarantee this is what's going on. Here I'm inferring what might be going on if I have a reaction that is either irreversible or far from equilibrium.
Sorry, I can't read what's underneath enzymatic or catalytic mechanism. What's underneath?
Conservation of enzyme or surface sites.
I have a question for the rate. The rate of reaction is like first it's slow and then it's constant and then it goes up. But,
Wait, slowly.
Yeah,
First, what does first mean? Are we talking about low concentration or short time?
the two mechanisms, just what you were explaining.
Yeah, so you're looking at the top curve or the bottom curve?
Do they belong together? Those two curves, do they belong together?
Yes, these curves belong
So
together.
the CA first, it goes down in a steep way. Well, for me, the bottom figure would mean that RA is first high and then goes down because the slope.
What does first mean? At short time or at short or low or high?
For me, on the CA, there's a steep graph. It seems like RA is decreasing because the slope is first very steep and then the slope is going.
No, what I want you to look at is the functional form. When you have a first order reaction, I mean, I could have drawn this more steeply, if you like.
Because for me,
The
it would be
point-
like first this one and this one.
Okay, the point is, when I have a first order reaction, we know that the concentration decays exponentially. First order reaction. An exponential decay, whether it's the exponential decay looks like this or like this, depends on the time constant of the or the e to the minus kt, depends what k is. So whether it's sharper or more relaxed depends on the constant, not on the form of the reaction. When I have a zeroth order reaction, that means the rate is zeroth order, so the concentration goes down linearly with time. Again, whether it's a curve that looks like this or a curve that looks like this depends on what the coefficient is. So here, what I'm showing is trying to show is something that starts out exponentially and then goes linearly. But whether this is sharper slope than the tangent to this curve depends on the constants. It doesn't depend on the forms. Is that clear? Are there other questions? Okay, so if you remember, until now, we've spoken about, we've always made the constant density assumption while looking at the integral method analysis. Now I'm going to spend a couple of minutes looking at a variable volume reaction. Are there any questions on all this algebra? So let's now get rid of the constant density assumption. And let's look at a variable volume batch reaction. Non-constant density. What physical situation would give us a non-constant density reaction? So I have to do that. What would cause the, what physical situation would give us a non-constant density? A gas reaction with what? What has to happen in a gas reaction to change the volume, to change the density?
Increase more, produce more moles of.
I produce more moles, or I heard another answer here.
Non-ideal. Non-ideal.
This could be expanding.
Why?
Pressure.
Heat. I might have an exothermic reaction that heats up the system. So that's another reason. Okay, so let's see what happens in those situations. Well, if you remember, we have our general equation, the one that functions like Newton's second law, was the rate equation. What is that equal to? RA is equal to? Now that's the constituent equation. What is the general equation that I was on?
1 over V, dna.
1 over, good. 1 over V, dna. And when we had constant density, we said V was constant, so we can move it in here and make VCA. Not constant density, I can't do that. So, how can we treat these kinds of situations? Well, if the change in volume isn't too drastic, then we often we can guess that the volume expansion might be linear in XA. Now, why is that? Why is that reasonable? Well, it's reasonable because I have some general function v of xa. And from calculus, if v is differentiable, v is infinitely differentiable, I can always expand it in a Taylor series. So if I write out a Taylor series, I have v0 plus, or why don't we say v at xa equals 0. Plus dv dxa at 0 times xa plus higher order terms, d squared v dxa squared at 0, xa squared plus dot dot dot. And if I truncate, so as long as xa is not too big, I can truncate this here, and I can call this thing epsilon sub a. And then I write v at xa is equal to v at 0 v at xa equal to 0 plus epsilon a xa. Now what is xa equal to 0? Remember, xa was defined by the relationship Na is Na0, 1 minus xa. So xa is always defined relative to the reference state. I have to define an Na0 in order to define an xa. When I change Na0, I change the definition of xa. So xa is defined in such a way that when xa is 0, Na is Na0. So therefore, v of 0 is v when xa is 0. When xa is 0, Na is Na0. So there's nothing wrong with me writing this V sub 0 because that corresponds to the reference state. Because the reference state is when xa equals 0. I'm sorry I'm fussing about the reference state, but you see, it's good to distinguish between the reference state and the initial state later on. The books don't seem to fuss about it. Maybe I just like to fuss. Okay. So, now I think there's just, in the definition of xa, of epsilon a, I think I'm not going to call this F, I'm going to call this V of 0 epsilon a. So I'm going to call this is a constant, and instead of calling it epsilon a, I'm going to call it V of 0 epsilon a. So that changes the definition of eps. So I have V0 times 1 plus epsilon a exa. And epsilon a is called the coefficient of linear volume expansion. Yep.
That V of 0 is not a reference state, initial.
No, I just went through a whole argument saying that V0 corresponds to the reference state.
V of 0.
As I said, V of 0, the whole argument I made for the last 5 minutes was to show that V of 0 refers to the reference state, not the initial state. That xa equals 0 is not necessarily the initial state, it's the reference state. So V of 0 is V at x equals 0, not V at t equals 0. It may happen to be t equals 0 if I choose the reference state as the initial state. But it corresponds to x equals 0, not t equals 0, which means the reference state. Okay, so I can solve for epsilon a. Epsilon a is equal to, I divide by V0, and it's 1 minus, so let's see, in order to solve for epsilon a, let's look at what happens when xa equals 1. When xa equals 1, then I have V of 1, and maybe I should be explicit here so we don't have this confusion, at xa equals to 1, is equal to V0, 1 plus epsilon a times 1. Xa equals to 1 is complete conversion. So I have V of 1 over V of 0 is equal to 1 plus epsilon a. Or epsilon a is equal to V of 1 minus V0 over V0. Where 1 means xa equals 1. So this tells me a simple way of calculating epsilon a. Epsilon a is V of 1 minus V of 0 over V of 0. What does that mean? That says, what is the volume of the system at complete conversion? Complete, meaning xa is used up. What is the volume at the reference state divided by the volume of the reference state, which by definition means it's 0 conversion. Okay, so let's see, look at an example. Let's say I have a reaction. A goes to 2B. No inerts. And let's calculate epsilon a. I have no inerts. So I have 1 liter of A to begin with, and nothing else. And that's at my reference state. My reference state is my initial state. I'm setting up the experiment. And I start out with 1 liter at the reference state of pure A. How many liters do I have if I convert all the A? And it's gas, an ideal gas. So here's the reaction. Remember, if I call on you, it's not a trick question. I have 0 liters. How many liters do I have reaction mixture? 2. I start out with 1 liter, I react with 2 liters. Remember, if I'm calling on you, it's not a trick question. If I ask for a volunteer, there might be a trick. So what is epsilon in this case? 2 minus 1 over 1. Well, let's say I change this, instead of no inerts, I have A goes to 2B with 2 liters inerts. And 1 liter A, and 0 liters B initially at reference date. Same reaction, but I put 2 liters of inerts in. So how many liters do I start out with if T is equal to 0? 3. And how many liters do I have at the end at full conversion?
5.
No, we're going in order. Actually, what's at the end? I start out with 3 liters at the reference date. I run the reaction. How many liters do I have at the end of the reaction? I use up all the ends.
5?
4.
4. How do you get 4? Just
Because you have 2 inerts and you have 2 B.
So 2 plus 2 is 4. What is 2 plus 2?
4.
So what is epsilon A here? Fire math? 1/3. So what you can see is that the epsilon A not only depends on the reaction stoichiometry, it also depends on what you put in the initial state of the nerves. Okay, so now let's look at a couple of, now let's see what we can do with that equation.
Whenever you add inert, you don't put it in, you don't put it in the equation, or
I don't put it in which equation?
in your reaction equation?
No, this is stoichiometry. Stoichiometry is telling me how much is changing. You can put it in, but you don't have to, because they're inert. For example, if I run a reaction in the laboratory, there's air in the laboratory. If I put the air in, if it's not involved in the reaction, I could, it doesn't change, or I don't have to. If I have a catalyst, I have to put it in. But air, if it's an inert is not a catalyst. Presumably, inert means I'm intending that it doesn't affect the rate of reaction, other than by diluting the concentration. I start out with 2 liters of inerts. That doesn't change. That. I start out with 1 liter of A. 1 liter of A turns into 2 liters of B. So at the end of the reaction, I still have 2 liters of inerts, I have 2 liters of B, and no liter of A. So 2 plus 2 was 0. Okay, so now let's go back to this. 1 over V dNA dt, V, we said, from here, is V0, 1 plus epsilon A xi for linear volume expansion. Remember, this doesn't have to be true. I might have a situation where I need the next term, but in simple situations, I can get away with the linear term. And there are a lot of reactions where it really is linear. Many reactions it really is linear. So it's exactly linear. If I have an ideal mixture, then it really is linear. But if I have non-idealities, it might be non-linear. Okay, dNA dt. dNA dt, now that's just minus Na0 dxa dt. So immediately I can see that this is equal to minus Ca0 over 1 plus epsilon A xa dxa dt, because Na0 over V0 is the concentration of the reference date. And this, again, remember, this is my general equation for any reaction, for any specific situation. I still need a constituent equation. K of T, F2 of C. Let's look at a few examples. Well, actually, before I look at example, let's just rearrange this. So I have, from this expression, I can put the xa's on one side of the equation. I have dxa over minus Ra 1 plus epsilon A XA is equal to, so I've kept the dxa, the 1 plus epsilon A XA minus 1 the RA, that's just equal to CA0, and let's keep the CA0. Well, that's not. Let's just notice that this is equal to dt over CA0, which I can integrate from XA of 0 to XA of t. 0 to t is t over CA0. So this is my general equation. And for any reactions, I put in the constituent equation. Now, of course, I'm assuming that I can, RA allows me to separate variables this easily, that I can write RA only as a function of x. Now, I want you to notice that this, so here I've assumed, this assumes, this separation of variables assumes that RA can be written as just a function of xa. Now, but this is also true, this form of equation. This also works even if I have a non-isothermal reaction. So note that if RA is RA of XA and T, so it's a non-isothermal reaction. For example, I have a heated reaction. I have an adiabatic reactor. So I insulate the reactor. There's a heat reaction. As the reaction proceeds, the reaction mixture heats up. As it heats up, I change K of T. What do I do? Well, if I can relate T as a function of XA, then this reaction, this expression, will be in this form, because I'll be able to write T as a function of XA. What equation gives me T as a function of XA? What gives me T as a function of XA? We did this earlier, we already asked this question 3 times this semester. Volunteer? T is a function of, how do I get relate T and XA?
T and XA is the concentration, so the energy balance.
The energy balance, the energy equation, the heat balance, the enthalpy balance, is a relationship between the temperature and XA. So if I include the energy balance here, then this also holds for non-isothermal.
Are you saying that RA is not a function of T?
No, I didn't say it's not a function of T. It is a function.
Not that T, the time.
Explicit function of time. Explicit function of time, not implicit function of time. Clearly, it's an implicit function of time. It's not explicit. It's a function of time because XA is a function of time. It's not independent. It's not on its own a function of time. It's via T and XA. Otherwise, you wouldn't have an equality. Any other questions? Okay, so I need a couple of auxiliary equations to, if you remember, my rate functions are going to be a function of CA. So I would like to relate CA to XA. So let's note that CA is equal to NA over V. And NA is NA0, 1 plus epsilon XA. And V, I'm sorry, 1 minus XA. And V is V0, 1 plus epsilon A. Where all I've done is I've copied over the definition of NA in the numerator and the definition of V in the denominator. And what did we say NA0 over V0 is? What is NA0 over V0? You're not paying attention. Concentration of the reference. Okay, again, if you're more concerned with writing than you are with listening, go to secretarial school. Don't go to science. You're supposed to be listening here. That's your number one job. More listening than writing. CA0, 1 minus XA over 1 plus epsilon A. So, since this expression is in terms of dxa, and my rates are usually in terms of CA, let's relate CA to XA, XA to CA. So CA is CA0, 1 minus XA over 1 plus epsilon A XA. And let's just invert that, just so we have it. We can do the algebra. We have CA over CA0 times 1 plus epsilon A XA is equal to 1 minus XA. So I multiply through by this. So I have CA over CA0 plus epsilon A CA over CA0. XA is equal to 1 minus XA. So I'm going to bring this to this side of the equation and this to that side of the equation. So I have XA is 1 minus CA over CA0 divided by 1 plus epsilon A CA over CA0. So if I ever need a relationship, I have both directions, CA in terms of XA and XA in terms of CA. Just a little bit of algebra. And now let's go through and do a few examples here. So let's first look at zeroth order. What does zeroth order mean in terms of RA? What is minus RA if I have a zeroth order? Just K1. So let's plug in a K1 here. And I have T over CA0 is equal to the integral 1 over K1 dXA over 1 plus epsilon A XA. And what do I get here when I take this integral? First, your name. So you get that right. EJ. Okay, so you got your name. EJ. So you got your name right. Now, epsilon A XA.
Epsilon AXA.
Constant. Where's the constant? Divided by epsilon A. So I have 1 over epsilon A A1 log 1 plus epsilon A XA of T 1 plus epsilon A XA of 0. Now here I have XA of 0, not XA of 0, because I might start the reaction at a place differently from the reference state. That's why I'm keeping XA of 0. So again, notice here, this is a zeroth order reaction. Zeroth order, and the answer is a log, because it's non-constant density. In other words, I can note that I have 1 plus epsilon A XA over 1 plus epsilon A XA of 0 is equal to e to the epsilon A K1 T over CA0. That's interesting. When I have non-constant density, I get an exponential, even for zeroth order. With constant density, I only got exponentials for first order. Let's go to first order reaction. First order minus RA is equal to what?
KCA.
CA. And CA, we know from there, is CA0, 1 minus XA over 1 plus epsilon A XA. Let's plug in. I have T over CA0 is equal to the integral XA of 0 to XA of T. By the way, notice, this is a zeroth order reaction. We got an exponential, but there's still a CA0 here. Remember I told you in first order reactions, there's no CA0. So now we know what to look for here. So let's see what happens here. Here I've got dXA over 1 plus epsilon A XA times minus RA. Minus RA is CA0, 1 minus XA over 1 plus epsilon A XA. And notice the CA0s cancel out, as promised. In first order reactions, they always cancel out. But not only that, this cancels out as well. And what I get is I just have dXA over 1 minus XA, which is the log. So I get minus the log of 1 minus xa of t over 1 minus xa of 0. And I lost a k. There was a k, k1. Or 1 minus xa of t over 1 minus xa of 0 is equal to e to the minus k1t. And notice here I have the minus. It's an exponential with the minus. And just to make this recognizable, I'm going to multiply top and bottom by na0. If I multiply by na0, na0 1 minus xa is just na. So this is just equal to na0, na of t, over na of 0 at t equals 0. And that's equal to e to the minus k1t. And I want you to compare that with constant density. If you look back, I had Ca of t over Ca of 0 was e to the minus k1t. Here it's non-constant density, so it's in terms of Na, not in terms of Ca, because the volume has also changed. Okay. Of what? K1 Ca0 1 minus xa over 1 plus epsilon axa times 1 plus epsilon ax. How about second order? Other questions? Second order. So I have T over Ca0. Well, first, what is minus Ra for second order reaction?
K1 CA squared.
K1 Ca squared. So let's plug that in. So I have T over Ca0, the integral from xa of 0 to xa of t, dxa over K1 Ca0 squared, 1 minus xa squared, 1 plus epsilon a xa squared, 1 plus epsilon a xa. And let's see what cancels. The Ca0 cancels, but there's still one left. And one of these cancels, 1 plus epsilon axa. And I'm still left with the integral xa of 0 to xa of t dxa, 1 plus epsilon axa. This is in the denominator, so I bring it to the numerator. Divided by K1 Ca0 1 minus xa squared. So I just need to integrate that, and then we're done for today. So, first thing, I'm going to move the constants out. So I have K1 Ca0t is equal to something. And I've got the integral, I'm not going to write the limits 100 times, dxa over 1 plus epsilon a xa plus epsilon a dxa times xa. Now you get this wrong. It's 1 minus xa squared over 1 minus xa squared. And first I want to integrate this, the second one. The first one's easy. So the second one I'm going to do by parts, integrate by parts. So I'm going to let this be dv and this be u. So du is dxa, and v is 1 over 1 minus xa with the minus sign. Why is that? Because when I take the derivative, well, actually, I may not need the minus, I don't need the minus sign. When I take the derivative, I get minus 1 over 1 minus xa squared times another minus 1. Okay, so this integral is just equal to uv, so xa over 1 minus xa at the limits, minus the integral of the du, minus dxa over 1 minus xa. Okay, so let's integrate. So this is an epsilon a. And let's see what I get here. What is the integral of xa of 0 to xa? What is the integral of dxa over 1 minus xa squared? We just said it as we did it from here.
Minus 1 over 1 minus xa.
There's no minus, just 1 over 1 minus x. It's the chain. So I have 1 over 1 minus xa of t minus 1 over 1 minus xa of 0. And now I have plus epsilon a times this evaluated the limits, xa of 0, xa of t. And what is the integral here? What is this integral? The integral dx over 1 minus x.
And then 1 minus xa.
And that takes care of the minus sign. So I've got, this thing gives me with minus sign, it's the log of 1 minus xa of t, 1 minus xa of 0. Okay, so let's put it all together. I have k1 ca02 is equal to 1 minus 1 minus x, 1 over 1 minus xa of t, minus 1 over 1 minus xa of 0, plus epsilon a on xa of t over 1 minus xa of t, minus xa of 0 over 1 minus xa of 0, plus the log 1 minus xa of t over 1 minus xa of 0. So what you can see is this, it's a little more complicated, but it's not that bad, it's just a little bit of algebra. You have xa of t here, 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 and here. But this is an expression for how xa of t varies with time. Notice that for a second order reaction, it was a little more complicated with variable volume than it was with constant density. Now, we've just done irreversible 0th, 1st, and 2nd order. Really, you can do this for any other mechanism, just you have algebra. Are there any questions on this?
When you said that you could do it between
Why couldn't I use the equation of state? Because the equation of state is also part of it. But the equation of state relates the temperature, the pressure, and the volume for a given composition. The energy equation, the reaction, gives you, when the reaction proceeds, you're changing the composition. So the equation of state doesn't give you enough information because you also liberate heat. So you will need the equation of state as well, implicitly. But you need the heat equation because the heat balance tells you how much heat is liberated as a function of reaction. It also tells you, you also have to change the composition, which thermodynamics will tell you something about. But you need both.
So when we
That
get
was a question. That wasn't a question.
Finish answering?
That was a good question.
So how would we got this for a second order change in volume reaction rate. How do we plot, how do we tell whether our data fits that? I mean, do we take that, is that a linear? Linear at all?
Stay all over the place.
Yeah, that's what I'm saying. So how do we know whether, I mean, do we plot it against the data that we have? And we
You
can
can't always get a linear relationship. You might manipulate this into another form, but how do you do it? Well, you have an equation, T versus XA. There's no equation for XA versus course, it's transcendental. You've got XA in the log and XA